for a few minutes. And before I dive in, how many of you are actually in the midst of rolling out V6 or already have deployed V6 in places in your backbones or networks? And how many of you are already starting to deal with any of the transition technology choices? Okay. So, and I'm actually going to be going through all of this, and we'll probably be done early because my expectation is that once we go through this, there will be more detailed questions about either individual technologies or some of the trade-offs. So I've actually sort of built that in, and I'm hoping to have the discussion. So if you are sort of looking through and looking at it, we will be having a question and answer at the end. So IPv6 is any day now rolling out. And the IETF, in its infinite wisdom, decided that back in '98 when they finished it, they said, and then of course in 2003 when they finished DHCP v6, were sort of surprised that the world didn't dive on all of it. And so they, I guess, decided that we needed lots and lots of help in coming up with interesting new ways. So there's an old joke from an Andy Tenenbaum networking book. The nice thing about standards is that there are so many to choose from. And the other part that usually doesn't get added, but is even more apropos in this case, is, and if you don't like it, stick around, it'll be different next year. And so, unfortunately, what has happened is we have a wealth of transition technology choices. And when you first start looking at all of them and you start reading through, and about the third one in, your eyes start to glaze, and you start trying to pick out what's actually different, and you get to this point where you start thinking, you know, I'm pretty sure I've heard this before, and I'm not really sure what's different about this one or that one or the other one except the name, and I'm not really sure which one fixes the problem I'm trying to solve. So what I'd like to do is basically break down what fundamentally is lying under the hood of all of them, come up with some descriptions and examples of, for those types, what actual implementations there are, and then sort of how do you individually go through, figure out what your pain points are, and then decide what actually may be appropriate for you. There are a couple of things, though, that I really do like to stress. One of the things to remember is that this is transition. It is not permanent, we hope. In internet terms, I suspect it probably will be, because my guess is that we will have a very long tail in corners of our network. But when I say not permanent and getting rid of, what I'm talking about is basically getting to the point where what you have left are these tiny little pockets buried in the corners of your network, in the same way that we still have AS400s and SNA and X25 and other crap buried in some wiring closet somewhere because we can't quite get rid of it. But hopefully sometime in the next 5 to 10 years we'll be at a place where V4 will very much be the exception and V6 will actually be the usable protocol. So that's certainly the first thing, is these are not an endpoint, they are a way of getting to someplace else. The other thing to stress is these should be your last choice. And as we go through the trade-offs with these, you will start to understand why. One of the classic things, of course, that marketing people hate to hear, but we engineers tend to say very often, is it sucks less. And that's pretty much the mentality that you're going to be having as we go through these. They do all suck. They are all compromises and bad choices. But also as network engineers, we realize that frequently we must do things that are not our first, second, or even 12th choice. It's more being able to make an informed decision. So it's the P's. This is basically what you do. You know, prerequisites. What are you starting with? What are your problems? Do you have partners or other people you need to deal with? And then finally, once you sort of scrape together all of your problem set, pick your poison. So the first thing, obviously, is you actually do need to know everything. And unlike most network upgrades, V6 is such a fundamental change that it pretty much pervades all of the layers, pretty much 3 through 9. And we will actually need to assist people with software, apps, development, all sorts of other things, and know what people are actually doing with our wire, because we and they can't just say, once it gets turned into a packet and gets spit out a NIC interface, it's a network thing, and when it goes back in the NIC interface, it becomes a system thing, and we don't really need to coordinate. There's an awful lot of visibility that must happen at both places. And obviously, you really need to know what address space v4 and v6 you are using, what types of addresses, how much of it is 1918 space, what are your requirements for doing some kind of address obscuring in v6, all of the other things, what are your subnetting schemes. One of the nice things about v6 is, for the first time in 15 years, if we call ourselves network architects, we actually can do a networking and subnetting architecture because we have enough address space. We can actually do subnetting plans as opposed to what do I have and how do I cobble it together. But when you're starting to think about transition technologies, you really should have a clear picture of what subnetting schemes you are hoping to get to first. And peering and connectivity. One of the unfortunate realities is that there is fragmentation in the v6 internet. HE and Cogent will not exchange routes. HE is willing, Cogent is not. Cogent wants a check. And this has been going on for over 2 years now, which means that as you are looking, you can't suddenly go to a provider and get a BGP feed or a default route and get to the internet. You actually need to dig under the hood with your peering and providers and make sure that across primary links and your backup links, there is some way to get to both of those chunks of ASs that both of them announce, or you will not see all of the possible v6 destinations that are actually on the internet. And again, what are they actually trying to do with the wire becomes important again. In v4, most of us are doing things with NAT whether we like it or not. So the answer is that there's a whole range of things that are just screwed. If you want to be able to do certain end-to-end or certain type of game applications or certain types of voice over IP or various other things, you're just stuck. And so the answer just is no. Well, users still want to do an awful lot of things, and with v6, we can start offering a lot of those services again, depending on what transition technologies we may be choosing. And we need to know what they're doing. And we do actually need to talk to the app developers who are doing our custom stuff and finding out what they are trying to do and helping them become educated. I mean, the sad reality is that there's an awful lot of things they're doing in v4 that are wrong in v4 and have never worked in v4. And some of these people, I talk to them and they somehow think that v6 will magically fix this. No, it will break in exactly or nearly exactly the same ways in v6. And in some cases, there are more possible vectors or exposed edges and surfaces against which you will pound. And even more so, there are things like QoS that potentially could work. There are tags and labels in v6 in the headers now. Potentially we could start to do that. Unfortunately, we're all living with everyone in the world with SDN and cloud and all sorts of other things, and they're saying we need to do all this magical stuff. Well, physical layer still matters. I don't care how many virtual machines you spin up or how magical the cloud is and how supposedly diverse it is. At a certain point, you cannot virtualize the speed of light. So, yes, disturbing but true. There are an awful lot of things with either financial or law enforcement or health or privacy that drive many of us with PCI compliance, HIPAA, Sarbanes-Oxley, law enforcement warrants, all sorts of other things. And you need to understand what information you are giving up or being unable to collect and provide depending on which of these transition technologies you may pick. And it is a network, and it's just like anything else. You're building a whole new network. It may wind up on the same physical layer. It may not. You may choose to actually have a different physical layer for your V6 and your V4, but in either case, you're building a network. How many networks? How are you subnetting? How many IP addresses are you burning? How many routing domains? How many OSs? What kind of routing aggregation points? All of these things are information that you should have before you dive in. The better informed you are before you start looking at these transition technologies, the more likely you will be to pick the less evil choice. And of course, what are your problems? What drove you to V6 in the first place? Are you actually short or out of V4 address space? If you're not a completely new business and you're in the US, probably not yet. But maybe you are. Are you trying to do V6 only networks? Right now that's particularly exciting. Not necessarily in the good sense of exciting. Other things that you may be dealing with. Again, those legacy apps, those OSs, those weird little boxes in the corners. Things that you don't have source code for anymore. Things that aren't under vendor contract because you bought your smart monitorable power strips 8 years ago and that company's not in business anymore. Well, you don't really want to replace all your power strips, or maybe you do. But you need to figure that out up front. And again, providing inferiority issues. Can you get to the whole V6 internet? Are you getting a good point? Is your subnetting scheme appropriate so that they will announce the prefix lengths that you want to announce? Right now, the equivalent of the /22 to /24 in V4, depending on your provider, of that's anything longer they won't announce. The /48 seems to be it. Well, a lot of providers give you a /48 as your chunk if you don't ask for more. If you've got 3 disparate sites, you need 3 48s. So you should be asking for at least a 44. And of course, we don't operate in a vacuum. We all have partners, either business partners or vendors that we deal with, or all sorts of things. And we can't control them. They have their own gear. We can't tell them what to upgrade to make our lives easier. Customer gear is a huge problem. CPE equipment is crap, and that's being nice. And it has been horrible in V4. They do fragmentation wrong, they do shitty firewalls, they are open resolvers, they fall over and die, they have really broken state table reversals, really crappy NAT. About the only thing that they do reliably is suck juice out of the wall socket. But you're going to have to cope with them. And we also all know that you can't tell your customers to replace their gear. And in some cases, even Comcast was trying to get past this. They offered to send people free gear to replace their CPEs. They offered to roll a truck and configure and install it for the customer. They offered iTunes cards and credits on monthly bills and the truck, and people did not want to upgrade. What do? Well, you live with it. Lack of vendor support if the company is no longer in existence. Or your company has decided that it's cheaper to have you as the support contract than the vendor, because they're already paying you and they don't care about your nights and weekends. These are all things that we have to live with every day, and when you're planning for transition technologies, we're the ones that will carry the pager and live with these decisions. So, time to pick your poison. So, there was a cartoon, and I couldn't find the actual cartoon, but it's a guy in an ice cream parlor. And he's walking into the parlor, and there's this sign on the wall with the list of all the flavors of ice cream available. Liver, wood chips, vanilla. We're all out of vanilla. V6 transition technologies, dual stack is the vanilla. And most of us don't have a choice and don't have the option of using it in a lot of places. So we're going to be eating an awful lot of wood chips and liver while we're going through. So here's where we actually get to go through. Fundamentally speaking, every transition technology, doesn't matter what they call it, what whizzy things they say, what weird pictures they put on the wall, it all boils down to one of these. Dual stack, you're doing some form of address translation, you are doing some kind of software tunnel, or you are encapsulating packets. Or you're doing a combination. There are several technologies that will actually combine several of these. And so when you're trying to reverse engineer what the hell transition technology foo is, and you actually start going through, very rapidly, when you read the fine print and you look at the pictures and all the rest of it, what you need to start doing is saying, which of those three last items is it, where, and write that in on the picture. And I'm next going to go through what are the known problems and trade-offs with those types of techniques, because all tunnels, regardless of what you call it and how you do it, will all suffer from the same classes of problems. So if you are dealing with something that will not tolerate one of the issues or problems that tunnels has, you have just figured out that anything that has a tunnel as part of its architecture is not a choice for you. So dual stack, this is, of course, the best understood. It's what most of the backbone providers have been doing for years. Even before Slack and DHCP were done, they just statically configured, they did dual stack. We know how it works. There are certainly issues, but we pretty much know what the issues really are. Nice things is there are no inherent end-to-end or logging problems as part of the protocol. You can introduce those problems yourself if you so choose, but they are not inherent in the design of dual stack. This is what the IETF recommends because it's easy and they think they're done. And if you can do dual stack, it also means that you can plug those boxes into a V4 or a V6 only network because you already know they work on both. And then all you're dealing with are the V6 only or the V4 only problems, which is a different problem. That's implementation's not, again, a shortcoming of that technique. But there are disadvantages. Of course, one of them is that means you have to have an IPv4 address for every box. And if you're going to V6 because you don't have enough addresses, dual stack is not for you. And we are just discovering what an interesting adventure doing V6 only is. There are any number of things that sneak back to V4, and if you're doing dual stack, you're hiding that. You are masking the issues. It's like taking cortisone shots. You are not fixing your bad knee, you just don't notice that you're tearing the cartilage every time you move until the cortisone wears off. You're also doubling your workload and doubling the number of places in which you, your staff, your process can screw things up. You know, doing ACLs in V4 is challenging. Doing a change that will affect the behavior you want correctly and not break something else or introduce new problems that you did not intend is very challenging. You're now doing it twice as often and you're doing it with addresses that are way harder to type. I will certainly put in the pitch right now. If you haven't come to some form of automating system for tracking your addresses and for generating configs, because it wasn't worth the trouble and it was easier to do it by hand in V4, well, we fixed that problem because it isn't easier to do it by hand in V6. Writing code is way more sane. Then, of course, the other problem with dual stack, if it was broken in V4, it will still be broken in V4, and you may be broken in two protocol stacks. Double the pleasure, double the fun. So let's now start diving into the three techniques and what are inherently wrong with those, which are address translation, tunneling, encapsulation. And we will start with my favorite, NAT. Yes. One of the problems, of course, with NAT is that NAT is inherently evil. It is a festering boil on the butt of our networks. Yes. I'm sorry to sugarcoat this, but they told me that I couldn't actually use any harsh language. So we all know and love the problems. It's hard to track who the users are at a given point in time. The logging requirements become painful. There are performance issues. There's resource exhaustion issues. We tell ourselves, or some people tell themselves, I try not to lie to myself, that it's okay with NAT because at least we're getting additional security, which is not true. The part of NAT that people think is security is not inherent in address translation. It is a stateful firewall that maps one address on a public side to multiple addresses on the internal network. And notice I did not say with private addresses. You can do this with public addresses just as well. The part that people claim is security is a stateful firewall that most NATs also implement. But NAT, as most people think of NAT when they say that, includes that. And because it is that conflation and all of those behaviors and all of those additional problems, I claim NAT is evil. It gives you end-to-end issues. It breaks apps. It breaks things with embedded addresses. So that's another. If you embed addresses in URLs and you expect it to work through most of the internet, I've got a bridge I'd love to sell you. There are logging problems, resource exhaustion, breaks IPsec, it breaks DNSSEC frequently, depending on what they're doing. Rate limiting and traffic shaping, all of those other things that you can in theory do with it, usually don't work well and introduce yet another whole set of problems and non-deterministic behavior that you need to figure out. There are a number of RFCs, some of which are specific to v6, some of which are also in v4, that basically explain problems with NAT. 4864 has a whole series of recommendations for things you should think about to have a more secure v6 network. And it includes a lot of these trade-offs with NATs as part of it. Excuse me. RFC 6296 is NAT-PT. The IETF in general tends to think it is smarter than the people who are actually trying to use the internet. And so when everyone said, yes, we know you think NAT is broken and you think that we should all do dual stack and end-to-end, but we have PCI compliance requirements and all sorts of other things, and we're going to have NAT in v6. And so the IETF sort of scratched its head and it went off. And so what it implemented, because everyone said it would be so much better, we know we're going to have NAT 6.6, we'd rather not have every vendor do their own way, let's just do an RFC, and you don't have to use it, but at least if you are going to have to use it, everybody's vendor will implement it the same way. And the IETF went trucking off, and what they produced was NAT-PT, wherein all you're doing is, if you look at most addresses, essentially the leftmost 64 bits, the first 64 bits, which is the network prefix portion in a standard subnet of a /64, and the rightmost 64 bits is the host ID, what they do is everything that goes through the box has the network portion for the internal side replaced with the external, which means you have a one-to-one correspondence and that internal host address is known, and you can get directly to them because when it takes off that internal prefix and puts the external one on the way out, on the way back it does the exact reverse, so you can get directly to every host. So the part of NAT that everybody wanted, which is actually stateful firewall, this is absolutely useless. And what they said was, what this is for is so that you don't have to renumber your network. Except most of us don't renumber networks all that often, and if we use GUA addressing, when we have the merger and acquisition problem, we don't have the classic, oh, we just bought another company that's also using net10, so which of the two do we renumber? Because if both of you use GUA, you don't need to. So NAT-PT was pretty much solving the problem that nobody had and failing to address what had been asked for. But you should understand what it is, because there will be people who will say, oh, why don't we just do PT instead? It's not the same. So tunnels. We all love tunnels because they have the oncoming trains. So again, these are all things, as soon as a tunnel is a virtual thing, and what you do is basically you configure two ends as, if I get it at this end, I'm going to skip the physical topology and ignore all of that, and I'm going to send it to the other end gateway, because that's what I'm configured for. And what I will do to get it through all of the intervening network is I'm going to stick state information around it. It really is sort of encapsulation, but it's a specialized type, and it usually has pre-configuration. So it means that you have abstracted the actual physical path and lost all of that information, including sizes of pipes and potential dealing with MTU and pipe size issues, and added extra state. So if I have a 1500 byte packet and then I stick it through a tunnel and other things have a 1500 MTU, it's too big, so I'm all guaranteed to fragment. And we all know that fragmentation works so well in V4. So maximum segment sizes, MTU mismatches, all sorts of other things, fragmentation and reassembly, all of those things are done badly even when you know the physical topology of the network and you can actually talk to every hop along the way and try and fix it. Because there are multiple apps that break MTU discovery, multiple people that filter ICMP in V4. Well, tunnels are yet one more way to add even more complexity and up the odds that you will be bumping into all of these. And in V6 you have the PMTU discovery problem as well, because it's the same thing. Unless both ends of the tunnel are correctly doing ICMP V6 with what the tunnel packeted size is, and of course vendors never write code that's wrong or fail to think about the implications, PMTU doesn't work. In all things, abstraction layers are useful if you understand what they are. But by definition, abstraction layers are opaque and hide the physical topology or underneath them. The advantage of a virtual is that you can ignore that topology and treat it in a simpler fashion. The problem is you only have the simpler information. There are a huge number of apps that are fundamentally broken. One of the other fun things is if you are doing tunneling where you are sending V4 packets over a V6 network in a tunnel, there may be translation and other fun things happening. So embedding V4 addresses as part of your V6 may complicate things. It also takes away that security by obscurity, because now I know what the 1918 address of that box is because it's encoded as part of the V6 address. And I know where it is because that prefix is being announced publicly. So there are unintended security disclosures when you do tunneling. There are things with routing loops and other various stuff with automatic tunneling, and we'll talk a little bit more about automatic versus static tunneling. And there's an RFC that details some of those issues. And they had one that was more generic that basically talks about tunneling in general, things that in V4 or V6 or, God forbid, CLNS or whatever, if it's a tunnel, there will be certain types of issues and certain types of security holes. If you do dynamic tunneling, this is where what happens is the gateway that you hand your packet to that actually has the tunnel that sends things out, you don't have to configure statically as your gateway. There are varying means by which you can dynamically find someone who's willing to take your packets, wrap the tunnel wrapping around them, shoot them out over that virtual link, and get them to the other end for you. Problem is, one of the means of doing that is Anycast. And of course, anytime that you do a routing reconvergence, Anycast hosts may change. So if you're in the middle of a TCP session and this router is the one you've been using and routing reconverges, and this is the one that's topologically close now, and my TCP socket is going here, no work. Also scales very badly. potentially. You need to think about all of your usage. And again, with you, it's the classic problem of, like with DHCP and having multiple DHCP servers, you have a power outage and half of your DHCP clients are now going to your other server. Can that other server actually handle that double load? You have to plan for all of those sloshes across your network. Alternatively, and we'll talk about one of the protocols that does this, you actually just throw it out and hope that there's somebody that has provided a gateway, and you have no clue of what their connectivity is, how reliable they are, and you can have horrible performance. And in general, if your capacity planning method is to chuck it upstream and hope that the guy upstream from you did a better job of planning, you may be in for some unpleasant surprises. And now the last of the three, encapsulation. For the most part, encapsulation and tunneling really are kind of the same thing. The difference is that encapsulation is less fungible in terms of having an obvious virtual pipe created. You can sort of let all the packets go wherever, and all of the packets have their own state. You don't necessarily have to have hard-coded ends that you were doing a tunnel with. But it's less fungible, but effectively it really is the same thing. You have something at one end that wraps stuff around your packet, shoves it off, and something at the other end that unwraps it and throws it onto the end wire, hopefully in the same state it was packed. So because you're doing that, you are going to have many of the same problems for many of the same reasons. Because you're adding size, you are disjointing the abstraction or virtual and the physical layers. You are making MTU discovery, maximum segment size, and all of those other things harder to figure out and easier to break. In addition, because it isn't necessarily a pipe, it also introduces more possibilities for packet insertion. You can do packet insertion attacks with a tunnel by, if I'm sending from A to B, bad person can just send traffic to B pretending to be A. And if it's UDP based, you may actually be able to correctly do the header stuff for the tunneling part as well, and you may be able to insert. But encapsulation tends to be a more open architecture, and it is more likely. The other, and usually the more fatal flaw, is this is one of those both ends have to agree and have software that matches and talks nicely. Tunneling, you throw it to another box, so you have routers or servers that must be upgraded or both talk, but all the end devices can be untouched. In encapsulation, usually you pick encapsulation because you want to push further and further to the edges and keep the complexity out of your core. But the cost is, at a certain point, there will come a box that would be where you would like that work to be done, but that you don't control that box. Might be a customer, or might be a CPU device. So, those are the baggage we start with as soon as you say, I am doing tunneling, I am doing NAT, I am doing encapsulation. Now let's talk about some of our spectacular choices. And starting with my favorite, once again, NAT. So, NAT 6.4 has actually been probably one of the more widely used. And in most cases, when you hear carrier grade NAT, when it first came out, carrier grade NAT was an oxymoron. It was a marketing term because it was a NAT, but if by carrier grade you meant that a carrier of large scale could use it and you could actually survive the abuse, that was not the case. There were a whole series of things it couldn't do or weren't functional in a true carrier grade environment. That problem has been fixed at a cost. But first, let's sort of go through NAT 6.4 and how it actually works. So if I have a V6 only client, which is very common these days with wireless networks and LTE networks, the handsets are V6 only because they couldn't get enough V4 addresses and they decided not to do NAT 444 and use 1918 space. So they actually did the less sucky thing. So I am looking for an IPv4 address, and I go to the DNS64 resolver. It'll actually go out on the internet, and it will actually try and resolve that, and what it will get back is a no data response. And in DNS, when I give a query and I get no data back, what the server is telling me is that label ip4.example.com does have data, but the resource type that you asked for, quad A, doesn't exist. And it's a hint that you can ask for other records in that label and get them. Well, it's a pretty good guess that most things that don't have a quad A will at least have an A record. At that point, it does get an answer back, and it gets a v4 address. Well, that's not terribly useful to a v6 only client. So what happens is the DNS64 resolver takes that address and it slaps a prefix in front of it, and it lies. It says, the authoritative server told me that the quad A record for that IP address is that v6 address. Your stack now has an address, so it makes a connection, and it hits the NAT64 gateway. And what the NAT64 gateway does is it looks and it says, oh, I see that particular prefix that's special. You know, wears a helmet, short bus special. And it strips that stuff off, and it says, that's a v4 address, and I will make a v4 connection, TCP off to that web server, and that web server will happily spew whatever content you are feverishly waiting for. And then that NAT64 box will then slam that prefix right back on, and that client is perfectly happy. And you can get to any v4 site that way. The nice thing is, if that DNS64 resolver looks for a quad A, and there was one, it can hand it back, and that client can make a v6 native connection. So it is quasi-dual stack. It has a v6 path, and it has a virtual v4 path. You can reuse the DNS resolvers because you can do a lot of queries for fairly low load, and as long as all of the NAT64 boxes all agree on the same prefix, you can have multiple NAT64s for performance and load sharing, and one DNS64 resolver, and it will work just fine. And with carrier grade NAT, most of the major vendors now have them. The downside is they are expensive. So the good thing is that you can now do v6 only everywhere for all your clients, for all that intermediate stuff, and get to a v6 internet and get moving towards actually being a real v6 only, and still support all of that content that is not yet available on v4. And there are a lot of commercial, or sorry, not on v6 yet, yes. There are a lot of commercial implementations, so you actually have choices, you have some negotiating power, and in most cases, because of the way they did things, initially there was very little logging, which meant that the law enforcement folks got very picky about that. Part of CGN also is they overbuild enough that it has the capacity to actually watch all of that stuff and track all of the state and log all of that stuff. So you can actually pass most of the security stuff. And you can do things with one-to-many if you want. Some will actually do weird stuff with trying to obscure client addresses. Depending on the box, you may still have some logging issues. The biggest thing is that you will still have all of the end-to-end issues whenever you're going through NAT, because it's NAT. NAT has not gotten magically better with v6. And there's a RFC that came out quite recently where some folks at Rogers and elsewhere did some testing, and not terribly shockingly what they discovered was all the things that were broken in NAT and v4 are still broken in NAT and v6 in the same ways for all the same reasons. So gaming, voice over IP, and various, all of that stuff, and you know, as I describe it, if you want to have that stateful firewall, you can get the lack of visibility, the operational complexity, the resource exhaustion problems, and the performance problems that you've come to know and love. They will all still be there for your enjoyment. It's not really any more secure than it was, but it's not any less secure. What may be an issue to some people is because your DNS server is lying, it breaks DNSSEC because DNSSEC is there to prevent people from rewriting your DNS answers before they give them to you. In theory, you could put your private key on or do something heinous with lying or other things, but effectively what most of the implementations do is if you say DO bit, I want DNSSEC as the client, and if it is signed coming in, they will not lie. You have to do something deliberately where there's a flag that usually says something like breaks DNSSEC, so you're aware of that issue. For better or for worse, since DNSSEC deployment is even less prevalent than IPv6, I'm not sure how much of an issue it will be for most of you. And tunneling. So, in the same way that you look at these transition technologies and you look at the IETF and go, please stop helping me quite so much. Microsoft was actually very active in v6 very early. They had the earliest v6 stacks of any client or host. They had the most RFC compliant. And they were the best about fixing things when they were broken earliest, and I love to bash Microsoft, so this is quite a concession on my part. Where they were a little less fun was in their usual Microsoft way. They decided that because they were diving in, once that's the flavor of Kool-Aid they like, you will be drinking the Kool-Aid. And so they came up with their own transition technologies because the IETF had not yet gotten on that bandwagon. And they had all sorts of things that are on by default. ISOTAP is one of those interesting little technologies. So basically what it allows you to do is have either dual stack or even v6 only clients, and you use some intermediate box as a tunnel endpoint gateway for you. And when you need to send v6 stuff, you just send it through. And then ISOTAP router can be dual stacked and will deal with all of that stuff for you. It is transparent to the endpoints other than that they need to configure it. You can turn it off in group policy, and that's what many folks do. But it's available. There are open source implementations, so you can do ISOTAP as a client with all of the major OSs, and it will happily work over a v4 network and allow you to bridge two v6 clouds over a v4 connection. It is, however, easy to exploit. One of the things that Microsoft did is, by default, as you're configuring things, once you've got your domain name and your suffix and your path and all of this other stuff as part of your, I'm configuring my box on my network and doing all of my AD happy horse stuff, you will, after you've been told you're in example.com, you will then do a DNS lookup to see if there is an isotap.example.com. If there is that DNS label with an A record, that is telling you that that is the IP address of your ISOTAP router. And you will happily enable ISOTAP, and you will start pointing all of your v6 stuff over that box. Now, kind of cool, but I'm a bad person. And my company lets everybody scribble their laptop's host name into my second level domain when I come up. So, I, being a bad person, will call my laptop ISOTAP. And I will get onto the network and I will use my AD credentials, and it will happily do the DDNS updates and use GSS tsig and validate it so I know that it's me saying I'm ISOTAP, except now I am a gateway router that everyone in the company will use. And I can do whatever I want to those packets for anything v6. It also does expose, because the way it works is it actually takes your v4 address and just munges some stuff in front of it, even 1918, or in this case, a PIPA addresses. So you know what the v4 address of that box is. You may or may not be able to route a packet to it, but you, as the bad guy, have gotten additional information that the company probably didn't want you to have. Teredo, another one that Microsoft went through, though they actually did get it through the standards process to some extent. And again, it's one of those, there is some form of NAT device here. I'm at a hotel. Well, that hotel probably doesn't have a choice of whether I want v4 connectivity or v6 connectivity, or whether I get NATed or rewritten or anything else, or what my DNS resolver is. I live with whatever bad choices that hotel made. But my company wants to use certain products that Microsoft has, including some stuff that uses IPsec secured encrypted tunnels over v6, which is a cool thing and which is secure. Well, what I can do is, if I, somewhere that is at least reachable on the internet, on the public v4 network, put a Teredo server, and I configure my client to use that, I actually build a tunnel that is invisible to this NAT device, punches through all of those, and I can have a v6 tunnel, and then I can layer IPsec and send things IPsec encrypted through that tunnel, and I have a secure connection everywhere. And there's no complexity for the user because they just do their AD login like they usually do for their mail. And if I happen to put a couple of extra flags on that say, by the way, when you log in, here's your printer, here's your DNS servers, here's your sus6, and here's your direct access server and your Teredo gateway, they don't know any better. It's all part of the whole Kerberized key exchange and token exchange from that ticket granting ticket, and it works great. So it works through anything. If I come to your network and you have firewall rules and all of the other stuff, it does not use a well-known port. It does not use a particular address. It does not use a well-known protocol number. So you are reduced to signature-based detection of this. So it will work through anything. Hotels, the rest, and there are versions for any Linux or variant, so therefore Apple, and for all Windows. The bad side of it is it works through any NAT or firewall because you can't detect it. So depending on whether you are on one side of the fence or the other, it is a really cool thing or a really scary thing. The other issue is Microsoft, to their credit, said this is a transition technology. At some point, v6 will be useful enough that this should go away because this is a suboptimal solution. They announced recently that they are going to sunset the Teredo servers that are publicly available. So at some point in the next several years, this will not be an option for most people. There's another interesting protocol called anything and anything. 6x is a provider. If you want to have IPv6 and your provider does not have it natively, which is very common for many people and has been for years, there are a couple of places that will provide v6 tunnels to you. One of them is HE, Hurricane Electric, but Hurricane Electric does it statically configured based on your public IPv4 address. So when I was living in Nevada, I was triply natted, and my public interface on my CPE had 1918 space address, which is not uncommon. So I did not have a publicly visible IP address. So I could not use HE or get a tunnel. Well, Jeroen, the guy who started 6x, thought that that was a bad thing and that there were a lot of people that were screwed that way and that they should not have to be a second-class citizen in being able to test and implement v6. So I don't know if he actually developed it or if he got someone else to develop it, but he helped promote anything and anything. The actual code is AICCU. If you want to install it on Linux, you can do apt-get or yum AICCU, and it will happily pull this stuff down. And then what happens is you register with 6x, and you can configure a tunnel where you use a login and password credential regardless of the apparent IP address that you're coming from. So I'm triply natted, and so I have no idea what IP address he will see when I actually make my connection to his box to open my tunnel. The way he decides that whatever that address appears to be is okay to open that tunnel to is by the fact that I have that login and password. Now the cool thing is that he routes a /48 to that tunnel whenever it's up, and it works from whatever address I'm on. So I now have native v6 at my home because I moved to Colorado, and I'm able to get it. But when I travel, I can use an anything and anything tunnel, and I can have v6 connectivity in my hotel room, because then similarly to Teredo, since it doesn't use standard tunneling, they don't block it, and I can get through. And so I can have a /48 in my hotel room, and as long as I do not bring more than 64,000 subnets worth of objects with me in my carry-on, I have enough address space. Cool thing is that it will punch through firewalls and all the rest, so you can use it when you travel. I love using it for labs for the same reason. Hotels and conference spaces frequently will give bizarre connectivity or do unpleasant things. Absolute worst case, I know that in anything tunnel will get out there. The client side is open source. The server is not, but the client side is open source. Problem is, it is an open source project. There is no commercial support, and 6X gets donated hardware. So the penalty in latency, because it is slower hardware, when I used to v4 ping my gateway from Nevada to Phoenix, which is where my gateway was, I would get 10 to 15 millisecond round trip times. If I ping 6 through that tunnel between the exact same two boxes, because it had to go through the tunneling software and all of the CPU stack and all of the other on his gear, I usually took about a 70 to 80 millisecond penalty on all packets. So it is not ideal for production, and it's a hard-coded end. If something happens and I lose my password, or someone else gets my login and password, that works. So not ideal in production. It's an interesting lab or personal technique. 6 and 4. It is an RFC. And basically what you do is you statically configure two IPv4 endpoints as the two ends of the tunnel. And then the v6 clients who put their v6 packets in v4, 6 and 4, will point at that gateway. This one actually does implement a protocol number in the same way that GRE tunnels are protocol number 39 or 40. There actually is an IPv6 transition tunnel number assigned by ICANN, protocol number 41. So if you decide you don't want people doing 6 and 4 on your site, this is actually one of those where you can actually filter because there is a protocol number. It does work through NAT more or less, and it's fairly tight header, so the odds are good that it doesn't fragment. The total payload in addition to the actual packet you're sending is something on the order of 20 bytes. So the odds are pretty good that you will not actually have to fragment most of the time, particularly if you're staying in the 1480 or less packet size. The drawback is that because of the way they do it with their tunneling, lack of encryption, various other things, it's not overly secure if someone can get into the path or can somehow inject packets. So certainly any UDP-based use of the tunnel should be considered untrusted. So those are some of the examples of tunneling technologies. Now let's talk about encapsulation. 624 and 6RD, which is a specialized implementation of 624, is the most common one you'll see. And again, what happens is essentially you discover a relay that will get your v4 packets out. You use public IP space as the transport. You can glue v6 clouds this way, and it will work. It is different than a tunnel only because these endpoints can change. The nice thing is that, unlike some other encapsulation schemes, because you are still chucking it to the nearest router that you have found, you don't have to change the client. So the client stacks will still simply spit packets and it will work. It is transparent. The problem is that if you can't control what packets your clients send out and they have access to gateways other than yours, or you didn't do gateways and they're just using whatever gateway happens to be lying around, you don't know where those packets are going, and you don't know who is doing that encapsulation and decapsulation for you. So aside from the security implications, there's also, again, if you're hoping that somebody upstream from you did a better job of designing the network than you did as your design, update your resume. Comcast, when they were initially rolling out V6, didn't have the code in all of their CMTSs everywhere. But they were very committed to trying to give people an opportunity to use V6, which was laudable. They did 624. Unlike the experiment in Australia, if you actually go and Google for Jeff Houston and 624, he talked about an experience in the Asian region where people just started throwing up gateways, which were sometimes someone's, Linux-based PC in their house behind God knows what link, and packet loss and performance was abysmal. You were getting up to like 40% packet loss on normal circumstances. Comcast did a better job of engineering, but again, the problem really is that it's essentially punting your problem to someone else with no control over your user experience or debugging. One of the other experiments out there was dual stack Lite, and a specialized implementation of that after. Again, Comcast, they had gotten to the stage where they were using Net10 as their customer aggregation fabric between the CPEs and the head ends and the actual real core routers. They had gotten to the stage of growth where they were on I believe it was their third Net10. So they had to have 3 sets of network monitoring tools and 3 sets of glass and hope that their NOC remembered which of the 3 Net10 addresses it was when they were debugging. And they knew it was just batshit crazy. So they said, what we should really do is figure out a way to do this so we can actually push V6 out all the way to the customer and upgrade our backbone to V6, and we don't have to do dual stack and all of that overhead. So the architecture that they came up with was this. And basically what you have is clients can be either dual stack or single protocol. But the CPE that's in the house, called the B4, they had fun that weekend with beers, takes care of taking that stuff, and if it's V6, it simply ships it off to the afterbox over a tunnel, and that box spits it out to the V6 internet, and it is more or less native. There's very little overhead. There is no NAT taking place. Nothing else is happening to it. If it is V4, it will actually stick that into a tunnel between the B4 device and the after device. It will encapsulate here. It will decapsulate there. Now, one of the things that you can look at is potentially if you don't need to use 1918 space down here because you have enough public address space, in theory you could actually not have NAT here in V4. Only encapsulation to get it from the B4 device to the after device. Now what they wound up doing was, of course, a NAT box because they did not have enough public address space to do this. But at least they had the option of separating out NAT from encapsulation. And this is the first example where you have 2 things. So at this point down here, if you're doing NAT, you now have added all the list of things that NAT breaks. And across here, you have the list of all of the things that encapsulation potentially breaks. So now you know what the trade-offs are. All you have to do is figure out this particular implementation does these 2 of the 3 possible choices, and you now understand your trade-offs and risks. And one of the good things was that you could actually do dual stack or V6 only or V4 only at the house. So all of the TVs and toasters and all of the other crusty shit that we all have around our house that will never get upgraded will still work. And it had commercial support in that they commissioned ISC, the guys who write bind and DHCP, to write after and the before stack, and they were actually using it with the OpenWRT, and so they were able to get commercial support for it. And you don't have to NAT. If you had enough before address space for all of the things behind the CPE, you could actually choose not to NAT. Of course, one of the problems with it, though, was multiple layers. You now have a virtual fabric versus physical fabric for your customer aggregation portion. You still have an actual core and internet connection. You have some complexity that you may have to debug in the customer's box, and there are multiple boxes, all of which are stomping on packets. Difficult for your NOC. And you have to replace that CPE, because you need something that can actually run OpenWRT, which is relatively inexpensive if you look at it from an operating system. But the reason CPEs suck is because they want to get them down to 75 cents worth of parts and pay some grad student a couple $100 to write a DHCP server and a DNS resolver, and then they can sell them at $5 a piece to the ISPs, who can sell them to customers for 20, and everybody's happy. And you have 75 cents worth of value. And at that point, they really do cheap out enough that you actually can't load OpenWRT in most cases. So suddenly you actually have to get into, God forbid, a $10 or $15 actual cost router. And you need to get them to replace it. One of the other ones that they did was MAP-E, which is mapping address and port pairs. Cisco started this because what they wanted was something that was relatively stateless and had less overhead than a classic CGN or NAT64, because they felt that that was expensive and that logging was problematic. And so their solution, rather than trying to just build big-ass boxes that were grossly over-engineered, which is basically how they did CGN, was they said, let's try and do a protocol to make this actually more sane. And then basically, again, what happens is you create these tunnels over which you send your v6 packets so that you can have v6 clouds traversing over a v4 fabric. Now, the cool thing is that it is relatively stateless, and one of the interesting things that they did was they said, well, that address plus port, which is really what you need in NAT, I don't want to do it in the big expensive device, because that's how you exhaust your CGN box. You have to keep state for lots and lots of customers all the time. Lots of memory, lots of some form of persistent storage, resource exhaustion problems, all the rest of it. If all you're doing is you're basically ripping something off and sticking something else on and shoveling it through, that's really fast. And if what you're ripping off and putting back on actually includes its own state so you don't have to pay attention, the big box can be much more simple and it can fit in the ASIC. And the CPE, which has a much lower traffic load because it's only that one house's amount of traffic and packets, can actually do that address and port mapping. Okay, clever idea. Interesting. But logging is still sometimes a problem, depending on how you choose to do it, and whether or not algorithmically derived mapping of address to who had it at the time is satisfactory for your privacy or security requirements or not. And we're back to, you have to replace the CPEs. So, that's the method. You start with, where am I? What do I have? What problems am I having to solve? What partner or connection issues am I going to have to deal with? And pick my poison. This is a dated chart. It's actually out of date now, but it shows you as an example. This was an exercise we actually did at ISC where we said, if this is my problem, do I need to have enough v4 address spaces? Do I need to have both ends actually running the same matching software? Is it something where I need to have an application level gateway? Does it break end to end? Do I have to replace a far end box? Is this my problem? And then all of the protocols, and you go across, and basically the way it works is if you need enough v4 address space, none of these are really an issue, or none of these are really an option. So I can actually sort of do a little spreadsheet, and I can go, here's my problems, and here's the things that are good and bad with tunneling, here's the things that are good and bad with encapsulation, here's the things that are good and bad with NAT. I cross the two streams, which is always fun because we know what happens when we cross the streams. We come up with a transition technology. And we find the one that for my particular problem in this instance, in this place, in this time, will suck less. And that's pretty much as good as it gets, I'm afraid. So right now, CGN is being used pretty heavily by a lot of the telcos and cellulars for new projects. It's starting to get used also by some of the data center and cloud providers as well, and it's all for the same reason. These are large numbers of devices that need addresses that did not exist before, and for which they do not have a huge stock of unused v4 addresses to just throw at the problem, and for whom NAT might not be a good solution, or for 1918 space. 6RD, which is rapid deployment, which is sort of it's a specialized way of how you have those dynamically assigned tunnel endpoints that you have in 6 to 4. And Free, who is a provider in France, used it quite successfully to rapidly deploy v6 across their whole backbone until they could do native. And as I said, Comcast did 6 to 4. They actually still have them. I discovered that when I moved to Colorado, I had what I had in my car. So I got my connection. I had a new DOCSIS 3 modem that I had bought at the Best Buy that Comcast said would work, and I plugged it in. And I had a little Apple Airport Express because it was small, and I figured that would get my phone and my tablet and my laptop all up. And I would have v6 and v4. What I discovered was Apple actually didn't do DHCP v6 correctly. So as long as I was using my Apple Airport Express, I wound up finding there were still 6 to 4 gateways on Comcast. As soon as I actually got a decent router that actually had a decent code stack, which was not made by Apple, I had native v6. So they are still out there. Japan, Swisscom, who recently went up, other people have used this as a stepping stone. And again, like I said, in that case, what's happening is they weren't depending on the upstreams, they were providing their own gateways to have at least some control over the experience, but it has all those trade-offs. And the ITF, let's chat for a minute about the ITF. So there are all these transition technologies, and they all evolved quickly, cleanly, and easily. As you can see from this slide, this is sort of the history of all of the little bits. And you can't actually read it well on here, but if you download the slides later, there are little things of who's using it where. And this is what we're left with. And from this, it's quite apparent, so says the ITF, of which transition technologies are appropriate for you. When I first started trying to teach and using this, that was basically the genesis of this talk, because my brain exploded. And I go to the IETF, and I have involved on these working groups and these lists, and I couldn't remember which one was which. And one of those classic stories, so originally MAP was proposed by Cisco, and they had two possible ways of doing it, one of which was with encapsulation, one of which was with tunneling. There was more enthusiasm for encapsulation, so that got the standards track draft, and MAP-Key was done as experimental. But as happens with engineers who spend time testing, working, writing code, and implementations, and all the rest of it, we all become very emotionally invested in our solution as the correct one. Now, the reality was that, functionally speaking, they were pretty much the same thing. I could actually show you the pictures of where it fractionally changes exactly where in the software stack you add and delete the wrapping, but basically it's identical. And they finally, after multiple years, got to the point where both of them agreed that yes, they were functionally equivalent and that either one had all of the same advantages and disadvantages, but neither one wanted to be the one that went away. So they did the only sane, sound technological thing that they could do. They flipped a coin. And MAP E1. So, oh, that's the, yeah, has the various, so there, a lot of these are actually done. They are deployed or deployable. Some of them are still being developed. And that doesn't even touch mobility. Now, working groups. I would encourage you, I mean, it's very fun for me and very easy to take pot shots at the IETF and say that they are a bunch of ivory tower folks who don't really care about our concerns and what breaks for us. And the IETF, when you go to them and say, you know, you guys don't take operational input, they go, no, we are a completely open process. Anyone can come and everybody is equal. So if you have concerns, you should come in. And of course, if you then do that, the reality is that there is a whole culture that you need to overcome, and you should be prepared to have a very thick skin and a lot of patience. But they are actually correct. And so one of the things I do is I try to be fair on both sides. You should go to the IETF, if you can, at least once a year. And while it is not quite as effective, the myth also is you don't have to actually go. If you simply participate on the mailing list, it is fully as functional. It's not quite. But it is 90 to 95% functional. So if you can't go, subscribe to the mailing list. Post on the mailing list, give them your comments, give them your feedback. We have no one to blame but ourselves if we did nothing and they give us crap that doesn't solve our problems. Now, if we give them input and they choose to ignore it, we have to push harder, but at least we are trying to move the process. And so these are some suggestions for some of the ones that I think are probably more relevant to this group. At this point, because V6 is becoming so prevalent in everything, when I go to the IETF now, I actually usually have to go to 10 to 11 different working groups because they all somehow touch V6. But the reality is that in this case, these are probably the ones that are most relevant. Softwire is, it's the soft wire, it's not a physical wire. So these are all of the encapsulation and tunneling technologies. So if you want to do nothing more than say, please stop helping us so much, if we see another V6 transition technology, we will kill you. Okay, Softwire is the group to come and say that. They do all of those. Sunset is the, how do we start turning off V4 over time so eventually it's mostly gone? What are the problems we're going to hit as we try and do more and more with V6 and V6 only? 6-man is the actual, this is the actual protocol. The actual IPv6 and DHCP, actually no, not the DHCP, it touches that, but all of these things like this is what's in an extension header, this is how an address is calculated, this is how you are supposed to handle prefixes. Anything that actually needs to change the protocol is in 6-man. Right now that's pretty stable because most of us are of the opinion that that's not what we need to do. Most of it actually is implementation dependent more often, and we're already way behind the curve. Actually spending the 2 to 4 years to revise an existing RFC that is an RFC, not a draft, is probably not worth the pain. V6 Ops is, in theory, the operational group. These are people that are using V6 in operational environment and have operational concerns. It is more operational than 6-man, and there are people in V6 Ops who really are clued, but there are enough ideologues who scream loudly that if you went to only one, that would be the one I would recommend going to. And then if you are in broadband or dealing with CPEs or end devices on a regular basis, HomeNet is, it's called Home Networks, but it really is essentially small, medium business and home. It's everybody that buys consumer grade gear, not industrial grade gear. So that's sort of where we are. Comments or questions? And the normal reminders, use the microphone, say who you are.
Bill Armstrong, Charlie. Well, check.
Hang on just a second. Can you light the microphones, please?
Oh, shut it. Bill Armstrong, Park Communications. We've got a conversation going on right now for Kim Company. And we kind of hit this point where we kind of make believe it and we're going to go do this MV6 thing. But the difficulty we've been facing with this our numbers policy in general, but one of the things we've come up with the run across is the concept of EULA versus EULA. And within, I don't know, Isaiah, he's another guy I work with, he and I kind of came to this impasse the other day about EULA versus EULA. Well, I mean, what everyone in here, what are your guys' thoughts? I mean, the more I look at the complexity of implementing EULA, the less it seems appealing. But it seems like a weird scenario to go global on, particularly for like private uses, things where we can serve with always use.
Right. So for the webcast folks, the question basically boils down to ULA addresses or unique local addresses versus global unicast or publicly routable addresses. To some degree, this is my opinion. There are some people that do debate this in the IETF or not completely agree with me, but first of all, what it is not. It was not designed to be the RFC 1918 replacement. A lot of people say unique local, never to be routed on the internet, and they go, oh, 1918 space. No, 1918 space was designed to have shared public addresses. It was specifically designed as a NATable stateful firewall address space to transition us until we got to V6. ULA was actually designed to not be connected. This is for nets, not that are natted or firewalled, but that are completely unconnected. A much better analogy would be the APIPA, the 169.254 addresses. That would be what they were conceptually used for. Now, the reality, of course, is that you can use NAT-PT or NAT and use them like you would use 1918 spaces. But my contention is it's much like thickening the rating of firewall. You still don't have a fireproof wall. You have the same problems, but you've increased the amount of time before you burn and can't get out. They are not guaranteed to be unique, so you still potentially have the problem of collisions when you combine networks from different companies. 6X is doing a registration process where you can have it randomly generate a ULA prefix and then it won't give that out again. So if you want to make sure that your ULA is unique, you can do that. But that's a myth because it's not guaranteed unique. It's guaranteed unique among all of the people who know about 6X and have chosen to use that. And some people use 1918 space because they don't want you to know what their addresses are, so they certainly aren't going to register those with 6X. And it doesn't solve the one-to-many problem of stateful firewall. So basically my recommendation is if you don't understand all of the complexities and have a decided need for which you will never have collisions, renumberings, or connectivity issues, and that's the problem you're trying to solve, then ULA may be reasonable. If you are not absolutely positive and do not feel like you know exactly why you should use it, then GUA is the answer. The one example I have ever seen that makes sense to me is we're getting to the point where there are networks with cars. You know, my car has so much stuff in it that I actually have multiple subnets in my car. And I drive it to the dealer and they plug it into a diagnostic machine. You really don't want to have to reconfigure that test harness. It would be nice to know that the carburetor was always 10.1.1.1. You obviously can't connect two cars together, but you never would. It's certainly never supposed to connect to the internet because you really don't want people on the internet talking to your carburetor. So in that case, it should never be connected, and it doesn't matter that every single one of them that comes in is the same. That's actually a feature. So to me, that's probably the only good use case I've seen for ULAs.
Brett Watson, News Star. I've asked you this before, but it's been a while. What about multi-homing? Is the IETF working on it, or are they just saying, sorry, you can't do it?
Do you mean multi-homing as in mobility?
Well, yeah, or just V6 routing in general.
Well, multi-homing is the same as anything else in the you get, two provider links or more, you get an AS, you do BGP or accept BGP announcements from, and V4 and V6 are the same conceptually. If you're talking about mobility of how do you handle the network as you move from one provider to another using your same address, the current mobility standards in IPv6 that are out and done do not scale well because it's the same thing as Anycast. Anycast is a phenomenally useful technique for doing things like root servers, CDNs, large 6-to-4 gateways, but we have a finite number of them. If every single house in the world tried to Anycast, the routing tables would explode. Current implementations of mobile IPv6 are the same in that they will work for certain applications where you can control the scale, but they will not scale to an unbounded internet. And we do not have a scalable unbounded solution that is an RFC yet.
Hi, Adam Galliano with Limelight. I'm primarily a transport engineer, so I don't have a lot of IPv6 experience, but something I've seen that I've always had a question about is the use of IPv6 addresses on point-to-point links. Like on IPv4, it's typically a /30 or a 31.
Yes.
But I believe I read somewhere that someone tried to specify a standard for V6 that stated that it should be a /64. Then I've also seen that some people are saying
No.
it should be a /126.
There is actually an RFC, and the recommendation is that you should use a 127. You can use a 126, but it leaves one or two of the holes open for some of the problem is that there are various ping pong and routing loop and other attacks where you can essentially melt the point-to-point link by getting a packet in and things bounce back and forth, and you spend all of your time playing with that rather than actually routing the packets that are supposed to be in the point-to-point. So originally there was a push for everything should be a 64, all subnets no matter how many, including things with only 2 possible hosts. And don't worry about wasting address space. People started saying, no, we should really use 127s to not waste address space, and that actually got squashed. And yes, I may find that an offensive waste of address space, but that isn't the technical problem. It is the security implications of doing it that make the difference. So the recommendation on the RFC is use a 127. What I say is that if you like the provisioning joy of being able to give a 64 to everything and that works for your provisioning system, you can assign a 64 to the link but configure a 127. The disadvantage with that is that sometime along the way, if you don't have automated bare metal provisioning, some network engineer is going to go, oh, that's a 64 for this link. They aren't going to think, and they're going to actually configure it as a 64, and that link will be vulnerable. The alternate, which is actually what I would normally think of doing anyways, basically you do 127s for point-to-points and 128s for loopbacks in the same way that you do 31s and 32s in V4. And what you do is for each single AS routing domain, contiguous routing domain, you assign a 64 for loopbacks and you assign a 64 for point-to-points. The nice thing is then you can do ACLs, because most permissions that you would want to enable or things you'd want to monitor, all your point-to-points are probably the same within that one routing domain. It also means that you can have one single ACL for allow this 64 for SSH and for to and from your network monitoring station, and you have one line. Again, I do stress one routing domain. If you actually have discontiguous space, you will need a /64 for each for loopbacks and for point-to-points. So one of those two styles will tend to work for most people. Most people who do more LAN and more host space will like the 64 with configure the 127 more often. Most people who do backbone and don't tend to deal with edges much and actually do 127s and 128s will tend to go that direction.
Thank you.
Sure. Other questions? Okay, then I think,
Alex Latsko, Server Central. One thing that was driving me slightly crazy now when cleaning up a legacy is those benighted sots who decided, oh, I can add V6, I'll just add family V6 to my BGP connection and throw the V4 address into the /96. Can we kill all of those people?
you bet. Don't quote me.
Unwinding, it's being fun.
Yes. There are a lot of bad habits that we will have to squash. So, if there are no more questions, tag me. I'm going to be out in the lobby and around for the rest of the thing. And thank you very much for your attention.